Okay, so like I said, here we are, part two. Kind of continuing on, we learned some of the basic internal anatomy here of how the nephron is put together. Now, when you think about what we're actually doing within there, and this is going to come back to two terms that we talked about at the end of the last lecture here: reabsorption and secretion. Again, this is just movement of stuff into and out of the blood and into and out of the filtrate, passing things back and forth. On average, right, again, remember, we're looking at a lot of fluid moving through, right? So 180 liters of fluid gets moved into and out and through the kidneys every day, right? This is blood basically being filtered. But you only make somewhere around 1.5 liters of urine, okay? So there's very much a selective process in terms of what do we pull out of the blood, what do we put into the urine, to kind of, again, maintain some volume there in your blood, in your circulatory system. So these processes begin with filtration. This is happening, of course, in the glomerulus and in the Bowman's capsule, okay, where we're literally just kind of forcing blood through some small holes. Because those holes are small, things like cells, things like proteins tend not to fit through it, so those things remain in the blood. But we lose a lot of water, and we lose a lot of small solutes, things like salts in particular. And so we create this stuff called filtrate. I won't write it out, I'll just underline it, which is water, is salt, is vitamins, can be minerals, can be all kinds of stuff, okay? Mostly just not big things. The second process then, the reabsorption process, okay, the directionality that we've got here, reabsorption and secretion, is basically from the blood's perspective, okay? So when we talk about reabsorption, this is the blood reabsorbing most of the stuff that we just squeezed out of it, okay? And this is a lot of it, right? This is like almost 100%, 99% of the stuff we just squeezed out, we reabsorb back into the blood, right? Again, primarily here in the proximal convoluted tubule, but it does happen in other places as well. Tubular secretion, on the other hand, again, remember, this is from the blood's point of view. So secretion here is getting stuff out of the blood and back into the filtrate. Right? So reabsorption is into the blood, secretion is putting it back into the filtrate. Ultimately, our goal through the processes of secretion and reabsorption is to take that original filtrate, okay, and turn it into a fluid that we call urine. And this urine ultimately ends up being less than 1% of that original filtrate. Almost everything that we make as that filtrate originally in the glomerulus, we pull back into the blood, right? All we really leave behind are waste products and a little bit of water. That's really all we end up wanting to put into this urine. Okay, so again here, basically a relatively simple cartoon, okay? We're not gonna see the whole thing here. We're really just seeing the first part of this. We've got blood flowing through here into our little glomerular capillaries, our little tuft, okay? And that tuft is surrounded by Bowman's capsule, okay? And this is where that filtration process begins. As we move down, the filtrate passes through the tubule, right? And we begin reabsorbing, so we pull 99% of the stuff we just kicked out back into the blood, right? Again, primarily in the proximal convoluted tubule, but it happens throughout the process. And then also, then we decide a little more specifically, okay, the stuff we just reabsorbed, what do we really actually not want? And we're a little more selective then in what we secrete back into that filtrate. Filtration is a passive process, okay? It just happens. Blood enters under pressure, not a lot of pressure, right? It's a capillary. It's not under a lot of pressure, but it's under pressure. And that little bit of pressure is enough to force fluid out of the capillaries, through the fenestrae, through the intercellular clefts, through all those little gaps in those capillaries, and out into this space here between the glomerulus, the capillaries here, and the capsule, the Bowman's capsule there. And again, it's just a matter of kind of filtering. It's literally just a filter for size, not anything else. And deciding I don't really want to worry about that. I'm just going to show you this basic little cartoon here. So here's our capillary over here, right? Our blood enters the capillary under modest pressure, right? And stuff that's in that blood then gets squeezed out through our fenestrae, through our intercellular clefts, through whatever, okay? And then here in the Bowman's capsule, again, we have another filter here from part of that capsular wall. Again, just the size. Anything that fits through these holes will enter into the filtrate. That's it. This means that big things remain in the blood. So cells, right? Big proteins, okay? But anything small, and 3 nanometers is pretty gosh darn small. Anything that's smaller than that will get through. So water, glucose, amino acids, broken down amino acids, vitamins, salts, all that kind of stuff will pass through there. Once we leave the capsule and we enter into the tubule, this is where we're going to begin this process of reabsorption, right? And again, 99% of what we just kicked out ends up back in the blood, right? Because again, it was just size. It was not a decision about whether we want or need this stuff. It was just size. So most of that stuff we do actually want, and we have to kind of pull it back in. So again, it is a little bit selective, but you know, it's such a broad selective filter that's really not. This happens both actively, so we do use some ATP to make this happen. It also happens passively. It really entirely depends on what our concentration gradient looks like, right? If our concentration gradient is set up the right way, we can do it passively and we have diffusion. If it's not, we have to use ATP to pump it back in. That's really all it is. It's not very exciting. And again, the idea here, there's a lot going on here. Again, just the basic idea behind reabsorption. That stuff that's in here, now in the filtrate, we want to bring it back into the blood. We want to reabsorb it back into the blood. How it gets there, really largely for our purposes, unimportant. In particular, one very, very important thing that we're going to be pumping back in is sodium. And the reason sodium becomes so important is that, as we're going to see later on, and we'll talk about this again, primarily I'll show you a video or a link to a video in the description here about how this process works, because I think it's a really wonderfully done video. Sodium is going to be the key to us concentrating our urine. So again, remember we saw before that your urine is somewhere south, right, of less than 1% of filtrate, right? It's highly concentrated. Most of the water, in particular, makes up the volume here. Most of that water ends up back in the blood, for, you know, obviously for good reasons. And so the way that we do that, the way that we concentrate that, the way that we pull water back out is through the action of sodium. Again, so sodium here really is the key to the whole thing. It's like Jar Jar Binks in the prequels. He's the key to the whole story, right? So we really need to worry about this really more than anything else. So generally speaking, we're going to try to get as much of this back in. So the primary active transport here is really kind of the big movement on that. Along with this sodium, okay, we can kind of piggyback on to this movement of sodium back in through moving things like sugar back in, some ions, so things like calcium, things like that, any vitamins we might need, whatever. We can co-transport those as we're actively pumping sodium back in. So again, really, really, really vital process here. If you remember one thing about this whole reabsorption thing, remember that it's sodium driving reabsorption of all of the other really important parts of this. Secretion, on the other hand, is, well, basically the opposite, right? We go, okay, we've moved the stuff into the blood, and so, well, we've made a terrible mistake, right? And now we need to move that back over here into the urine. We say, no, we really don't want this after all. So this is going to be stuff like potassium, free hydrogen atoms. We talked about managing acid-base balance in your blood. This is one way that we do that. If we're too acidic and we can't buffer, we can get rid of free hydrogen atoms that way, free hydrogen ions that way rather, and in doing so, raise the pH, lower the acidity. Things like ammonia, right, are nitrogenous wastes, are breakdown waste products of amino acids. Turns out to be ammonia. We got to get rid of that somehow. So we dump this into the urine that way. Things like creatinine, organic acids, bases, stuff that we just don't have any reason to have in our blood anymore at all. Along with our free hydrogen ions, we can also get rid of bicarbonate here as well. And again, this is all the stuff we don't want, right? Just stuff that is just not, we don't want anywhere near our body anymore. We got to get rid of it, okay? Drugs, excess products, all this stuff. The way in which we maintain concentration or remove concentration around has a lot to do with a process we've talked about already called osmosis. Here, however, the idea is slightly altered. We talk about the osmolality of our fluid rather than the osmotic pressure, but the osmolality. And really what the osmolality is, right, is can you cause osmosis? Are you likely to cause the movement of water across a membrane? Right, so the osmolality is measured as basically the concentration of stuff in water. So the higher thing moves, and I'm trying to write higher the osmolality, right? The higher concentration of stuff is, right? And the more likely to cause, right, to bring water into this fluid from another source. In our bodily fluids here, the term that we're going to use is milliosmoles, okay? And generally speaking, your kidneys are going to try to maintain an osmolality of your plasma at about 300 of these milliosmoles, okay? And we do so with something called the countercurrent mechanism. Now, what I'm going to do is I'm going to link to you in the description below a couple of really excellent videos that show this process, so that when we come back to my description of it with static things in the next video, hopefully it'll be just a review of some of those basic ideas behind what's in that. Okay, so we'll leave it there. We'll come back and we'll close off the section here, the chapter here with the next video, and then we'll move on to the reproductive system after that.